Okay, welcome my dear students. This new session. In the last class, I introduced the definition of a inverse of a linear transformations and nonlinear singular transformation. It is called as singular, non-singular when this is bijective. One and onto linear transformation is also called as isomorphism. In this session, we discuss some examples of a non-singular linear maps and try to find how to find the inverse of a linear transform. Let us begin with this problem. So there is a two way we can just solve this problem. Either we have to convert this map is defined into a, because you just said we have a we try to find out is a non-singular or not. Clearly you see this is the both the dimension of both the vector spaces are the same. So if dimension of both the vector spaces is the same, we know that the result we have a dimension of a v is the same as a dimension of a w. Then if t is 1 to 1, then t is on to, this is if and only condition is there. If t is 1 to 1, if and only if t is on to. If we have both the vector space linear transformation t from v to w, and both the linear transformation v and w are the same dimension. Okay, so we just say t of E1 is equal to this, t of E2 and t of E3 defined in this way. First we have to try to find the inverse. This transformation is a non-singular, so we have to just find the what is the kernel of this. So find t is we find the general elements of a u is the element of a x1, x2, x3, and this u can be written as a finite linear combination of the elements of a E1, A2. So u can be written as you have a x1 E1 plus I just say you can write u can be written as a finite linear combination of the basis of this art basis. You have a E1, E2, E3, and the basis of this is equal to these are the basis for this art. So we can just say t of E1, t of E2, t of E3 are the basis for this art. So u can be written as a alpha times of a alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3, and u is equal to this is simplify this is simply you can say that x1 E1, x2 E2, x3 E3. So we write into this form. So x1, x2, x3 can write into this form, and now we have to operate the t, and t of x1 E1 plus x2 E2 plus x3 E3, and now you know that the this t is we have a linear transformation. So this can be t of E1, x2, t of E2, t of E3. Now you have a t of E1 is written in the form I just said check E2 plus E3. You have a E2 plus E3. You have a t of E2 is E3 plus E1. Yeah, E3 plus E1, and then we have a E1 plus E2. So we have a t of E3 is equal to E1 plus E2, and then we have to write is that t of E1 is equal to you have a x1 E2 plus E3, t of E2 is equal to E3 plus E1, x3 is equal to you have a E1 plus E2. Now we have to write this all the coefficient gathering into this form. So this is nothing but is equal to you have x1 E2 E3 means 0 1 1 plus x2 you have a E1 E3, so 1 0 1 plus x3 is E1 plus E2, so E1 0, because we just said that E2 plus E3 can be written as a 0 1 0 plus you have a 0 0 1, this can be written as a 0 1 1, and similarly you can say that E3 we have a E3 plus E1, this can be written as a 0 0 1 E3, E1 is equal to 1 0 0, so this can be written 1 0 1, and similarly E1 plus E2 is equal to you have a E1 plus E2 is equal to, you have a 1 0 0 plus 0 1 0, this is 1 1 0 in this form. Now we have to write is this x1 is equal to 0, so you have a x2 plus x3, and then similarly you have a, clearly you have a x1 plus x3. Now you have a, clearly you have a x1 plus x2. So t of x1 x2 x3 is into a defined into a this form, though this can be written in the either write E1 E2 E3 form is not a problem. So this means we have to write into this form t of x1 x2 x3 in this form. So we see this means t of x1 x2 x3 is equal to this form. So this x2 plus x3 is a coefficient into this form. So we if t of x1 x2 x3 is equal to 0, then we have to just say that this is equal to 0, this is equal to 0, this is equal to 0, scalars are 0. So these three scalars are equal to 0. If we simplify these three scalars, you can see clearly x1 plus x3 is equal to 0. So x2 plus x3 is equal to 0. So this means we have a clearly you can eliminate the this x3 from here, x1 minus x2 is equal to 0, x1 plus x2. This means implies we can just say that you have a x1. If we have a x1 plus x3 0, you have a x2 plus x3 0 minus minus, this is cancelled out, x1 minus x2 is equal to 0 and x1 plus x2 is equal to 0. So this implies that we have a given x1 is equal to 0, and then x1 is equal to 0 implies that x2 is equal to 0, x1 x2 is equal to 0, this implies that x3 is equal to 0. So means we can say that clearly x1 x2 x3 is equal to 0. So the kernel of nothing was equal to 0 of a R3. So it means we can say that t is 1 1, and also directly we can also say that t is onto. Why? Because both the dimensions vector space has the same dimensions. So otherwise we can also try to find the v is equal to R3, then clearly t is onto, hence t is a non-singular and T inverse exists. So the first part of this problem we have to done, and the first part of this problem we have to just show that T is a non-singular linear transformation. Now if it is a non-singular, then we have to find the what is the inverse of this linear transformation. So finding the inverse, we have to take is a two method for finding the inverse of this linear transformation. One is the direct and another we have to write. So I just try to explain you both the methods for finding the T inverse which is also linear and 1 1 onto map from to this. We have a T of E1 is equal to this, T of E2 and T3 is equal to this. Then clearly we can say that E1 can be written as you have a T inverse E2 plus E3, and also you have to rather E2 can be written as a T inverse E3 plus E1, and also you have a E3 can be written as you have a T inverse of a E1 plus E2. Now because T we already show that the result T from lit if T is a bijective and T inverse is also is a non-singular. So if non-singular, then inverse is exists. So this means is also is a linear map. So this means this is we can say that T inverse we have a E2 plus we can say that T inverse of a E3, and this can be written as a T inverse E3 plus E1. This can be written as a E1 plus E2. So we have to find the values of a T inverse E1, T inverse E2, T inverse E3. And now you have a this is equal to 1, this is you have a 3, this is equal to 2. If we have to subtract 1 and 2, then we have to eliminating this you have a E2. So this means we can say that by this we can say that T inverse E1 minus T inverse T inverse E1 minus T inverse E3 is equal to E3 minus E1, and also that is the second one you have a T inverse E1 plus T inverse E3 is equal to E2. If you adding these two, this is simplified, then you have a 2 times of a T inverse E1 is equal to you have a E3 minus E1 plus E2, and then we can say that simply is equal to we can say that T or inverse E1 is equal to 1 by 2 minus E1 plus E2 plus E3. So, T inverse E1 is equal to this. Now, similarly, we can find what is the value for. So, this is this. Now, we have a simplify this. So, T inverse E1 is equal to this. So, this is nothing but is equal to value is equal to this. So, similarly, we have to like this. So, we have to T inverse E1 is substituting here. So, we just say that into this form T inverse is equal to 1 by 2. So, we just take a T inverse and E3, the relation is here, and then we have a relation is here. So, T inverse E1 plus, so you have a inverse plus E2 is equal to E2 is equal to E3, and now T inverse E1 we have to just say 1 by 2 minus E1 plus E2 plus E3 plus T inverse E2. So, this means is equal to you have a E3. So, T inverse of a E2 is equal to E3 minus 1 by 2 minus E1 plus E2 plus E3, and then is equal to 1 by 2 E1 minus E2 plus E3. Similarly, we can calculate T inverse of a E3 is 12 by 2 E1 plus E2 minus E3. Okay, so this means we have to substitute the value, and this is how this is come. We have to just say that is equal to 1 by 2 0 1 0, and then we have a plus 0 0 1, and then we have a minus 1 0 0. So, this is equal to minus 1 1 1, and then similarly this at this. So, T inverse E1, T inverse E2, T inverse E3 we have to calculating the value for into this form. Now, T inverse E1, E2, E3 can be written as a finite linear combination of x T x inverse is in the form of a this things. T inverse is a linearly, and T inverse x1, x2, x3 can be written in the form of a this form. And now substitute the value for x1. You have a T inverse is equal to you have a 1 by 2. You have a value is equal to minus 1 1. So, minus 1 1 1 plus x2 1 by 2 1 minus 1 1 plus 1 by 2 x3 you have a 1 1 minus 1, and then it can be share that this can be 1 by 2 is come outside. So, we have to just say that minus ka x1 plus ka x2 plus ka x3. Now, x1 minus ka x2 plus x3, and now we have a x1 plus x2 minus ka x3. So, this means T inverse we have a x1 x2 x3 is to this form. So, this we have to getting this is the clearly is a T inverse we have to obtain into the in this form. So, this is the one of the method we have directly. Another method we have to just using this we have assuming that this is the what I just said that. Now, another method is this we have to assume that T inverse is equal to some element y1 y2 y2. Now, by the definition of a T inverse, so T of y1 y2 can be written in this form. So, this is E1. So, we have writing this. So, this means x1 x2 x3 can be T of x1 x2 x3. This is x1 x2 x3 can be written as a T of this is y1 y2 y3. So, this is y1 plus e1 y2 plus e2 and y plus y1 y2 are the element of a v, and e1 e2 because this is y1 y2 y3 are the element of a vector space of a R3, and the basis spaces is we have a e1 e2 e3 are the basis. So, this y1 y2 y3 can be written as a y1 e1 plus y2 e2 plus y3 e3. So, that is why I just said that this is written in this form. Now, T is linear. So, this can be written as y1 T of e1, and then we can say that and so on, and then T1 e2 value we have to substitute the y1 e2 e and so on these values of the e1, and then we can write this simplify this y1. So, this is e1 is a y2, and then you have a y3, and then so this is a general T of this is x1 x2 x can be written in the form of a this form. So, this we have two equations are there. We have to find the values for y1, y2, y3 in the terms of x1, x2, x3. So we have 3 equations are there. So this is equal to 1, this is 2 and 3, and now we have to solving these 3 equations. So we have a y1 is equal to into this form. Just how to solve this is clearly we have a y1 plus y2 is equal to you have a x3, and then you have a y3 plus y2 is equal to x1. So we have to subtracting these two. So this is cancel out. So you have a y1 minus y3 is equal to x3 minus x1, and then you have a y1 plus y3 is equal to x2. So this is also x3 x2. Now these two gets cancel out. So y1 is equal to you have a 1 y2 sum of these two minus x1 plus x2 plus x3. So similarly we have to getting the y2 and then substitute the value for this y1, y2, y3 in this form here, then we can clearly get the inverse of this linear transformation. So now we have a try to explain you one more example. I just using always this second method. Now onward we have to try to find the inverse of any linear transformation. Okay, so determine the linear transformation defined by v1 plus v2, v2 plus v3. So r3 to r2 is a non-singular or not. So we have to clearly this both the dimension or not the same. So we have to check is 1 1 or on 2 separately. So we just find the kernel. So we have to first is a kernel of a T. By the definition, v belongs to the v such that T of v is equal to 0. So T of v is equal to 0 means we have T of v1, v2, v3 is equal to 0, and then T of v1, v2, v3 is equal to 0 means this is defined is a v1 plus v2, then v2 plus v3 is equal to you have a 0 0 because r2. So this is a v1 plus v2 is equal to 0, then we have a v1 plus v3 is equal to 0. So then we have a v2 is equal to minus ka v1 and v3 is also minus ka v1. So this means kernel of T is nothing but is equal to you have a v1 minus ka v1 such that v1 is the element of some r. So this can be written as a kernel of a T is nothing but is equal to, we can say that kernel of a T is nothing but is equal to span of we have a 1 minus 1 and 1, and then clearly this means span is a 1. So this means clearly we can say the dimension of kernel of a T is equal to 1. So dimension of a kernel of a T is equal to 1, then clearly we can say that this is a not a 1 1. So this means clearly not 1 1. So this is dimension is not equal to 0. So this linear transformation clearly is not a 1 1 transformation. So this means is not a 1 1 means clearly is non-singular, but we try to find the what is the it is onto or not. So this is clearly is a 1 1. Now we try also found the what is the possible this is onto or not. So let RT is equal to AB, T V1 V2 such that T of AB is equal to in the form of AB, and then we have to define we have a V1 V2 it define the form of a in the form of this V1 plus V2 V2 plus V3. So we have this is means V1 plus V2 and V2 plus V3 is equal to you have a AB, then V1 plus V2 is equal to A, then V2 plus V3 is equal to you have a B, and we have to simplify this in the form of a AB in the form of V1 and V2, and then clearly this is equal to A and B. So this is simplify this V1 is equal to we have A plus B by 2. So this is clearly V1 V2 is there. So V2 plus V3 is there. So we eliminating this. The V1 V2 can be written in the form of a minus V1, and V3 can be written as a B minus. You can just say that V2. The V3 can be written as a B minus A plus V1 in the form is of this form. So we just take a V1 is equal to A minus V2 is equal to V2 is equal to A plus B by 2. V3 is equal to B minus this, so B minus A. Now substituting these values into this AB into the R. So V1 R3 such that T of EV this RT is equal to we have a 2, then we can clearly say that this is a clearly this is a onto, and also by the rank nullity theorem we can say that dimension of V is equal to dimension of kernel of a T plus dimension of range of a T. Dimension of a V we have a already giving from map from V3 to V3 to R2. So dimension of a V you have a clearly dimension of a V's you have a 3, and dimension of a kernel T is equal to 1, and then we have to say dimension of a range of a T. Now dimension of a range of a T is equal to you have a 2. If dimension of a range of a T is equal to 2 means RT is clearly you have a R square, and this generated whole the set is there. So this means we can say that clearly this is T is onto, but T is not a 1 1. So clearly this is a non-singular, and we cannot find the inverse of such a linear transformation. So is this linear transformation we cannot find the inverse of this linear transformation. So this is a range of R2 onto, but T is we get T is onto but not 1 1, and T is not non-singular and it does not have an inverse. Okay, now one more example. If it is non-singular, then we try to find the inverse. In this case, clearly this is if you see this is T of V1 V2, again we define from this R3, and this is equal to you have a V1 V2 is equal to 0. So this is clearly kernel of a T look like is a 0. We can just take a T of V1 V2 is equal to 0 0 0. So this means we can say that so you have a V1 V2 0 is equal to 0 0 0. So this is means you can see V1 is equal to 0, V2 is equal to 0. So this means kernel of a T is equal to you have a 0 subspace. This implies T is 1 to 1. Okay, so clearly T is a 1 1, and because its dimension is 0, thus clearly if we rank nullity theorem we can say the rank dimension of a RT is not is equal to is maximum is equal to dimension of a 2. Means if we by the rank nullity theorem, dimension of RT should be less than equal to the dimension this is R3 because of so this clearly look like it's not an onto. Let's try it is onto or not. Okay, so we just try to this take this is clearly is trivial kernel of a set is at 1 1. Now we have a range of a T in the form of a T of ABC. By the definition from this T of V1 V2 is equal to this. So RT is the form of a B 0 0. A and B are the element of a R. So this is nothing but is equal to RT is span of RT is nothing but is equal to you can say that is the form of a 1 0 0, and we have a 0 1 0, and then you can see this is the span of this is clearly not generated the R3. So this is a proper subset of R3. So this means RT is a range of a T is a proper subset of a R3. So clearly this is a not onto. If it is not onto, then we can say that this is clearly is not a non-singular. If it is non-singular, then we can say that the inverse of such a linear transformation does not exist. So this means the subspace R3 is especially xy plane in R3. So RT is not equal to clearly R to the power 3. So T is not an onto, hence the transformation T is 1 to 1 but not onto. Thus this T is a non-singular and it does not have an inverse in this case, we can just say that. Okay, so this inverse does not exist. We can try to find the in this case. So this means clearly we say that this is clearly we can explain this in this session about the how to find the inverse. So I will take a two method. One of the method we just take a inverse of this subset. We have a any element of we have to just say suppose we have a R3 to R3. So we take a x1 x2 x3 in the form of a sum y1 y2 y3, and then we have to find the value for this can be written as a T inverse of a y, T of right in the form of a T of y1, y2, y3 in the form of a x1, x2, x1, x2, x3, and try to find the value for y1, y2, y3 in the terms of x1, y1, x1, x2, x3, and then substitute the value for y1, y2, y3 here. Then we get the linear transformation. So in this case, we have to this session we have to try to solve 2-3 problems related to the non-singular. One of them we have to show that the linear transformation is a non-singular, and then we can find how to find the inverse of a linear transformation. Another 2 examples. One of the example I choose where T is not a 1 1 but T is onto. Another case we have to choose an example where is a T is 1 1 but not onto. In both the cases T is a non-singular, T is not a non-singular. If it is not a non-singular, then we cannot find the inverse of the linear transformation. So I think I have to stop this lecture today into to this point, and in the next class we have to discuss about the some properties of this isomorphism, when we just said that this linear transformation is isomorphism or non-singular inverse of a linear transformation. Some basic properties and important result about the linear transformation T from V2 vector space Rn is also is an isomorphism. I just say prove into the previous one is a little bit about the sketch of this. In this class we have to prove this result when we have a linear transformation any vector space V2 Rn is always is an isomorphism. So that's things into a discuss into the next class. So I have to stop today's class here. Okay, thank you very much for this session. Continue in the next class. We have to some basic properties of a inverse of a linear transformation.